On behalf of SafeTraces, I'd like to welcome you to today's webinar on UVGI, and it's titled, How Does Upper Room UVGI Work, and How Do We Know If It's Working? We're very pleased to be joined today by an excellent panel who I will introduce shortly. I'm Erik Malmstrom. I'm the CEO of SafeTraces, and we are a California-based biotech company that has a novel technology for performance testing HVAC systems and air cleaners. And we work very closely with research collaborators and also with industry practitioners on taking a lot of the best research and science and putting it into real world practice. And so today's topic is something that has been very much on people's mind in the indoor air quality and energy worlds over the past couple of years. And we thought we could really help contribute to this discussion by level setting people on UVGI and then talking about how it works, how it interacts with mechanical systems, how to think about the different product types and their applications in real world environments, and then to get to the second part of our question, which is being able to verify that the units are working. So a couple quick logistical notes. We are going to try to make this interactive, but we have a lot to get through. So we're going to have the chat open throughout today's discussion. If you have a question, please put it in the chat and we will try to respond promptly on that. And I'm putting it into presentation mode now. So just put your questions in the chat. Unless it's very urgent, then we're going to hold it till the end. And then also today's webinar is going to be recorded. So we're going to send this out to all the attendees today, and then also those who are registered but couldn't attend, they will get a copy of this. So without further ado, I want to briefly introduce our panelists. So I'm your moderator. Our first panelist is Dr. Chip Blatchley, Professor of Environmental Engineering at Purdue. He is a world-class expert on UVGI and will be our first speaker today. Our second panelist is Dr. Bill Bahnfleth, Professor of Architectural Engineering at Penn State. He's also, Chip and Bill are both advisors to SafeTraces. Bill is an expert on indoor air quality and mechanical systems, and also has been very involved in ASHRAE, both as a former president and then the current chair of the ASHRAE 241 Standard Committee for the Control of Infectious Aerosols. Our third panelist is Bill Palmer, the president of Aeromed, who has for nearly 40 years been a real world practitioner on the front lines of deploying UV technologies out in real world environments, and is going to talk to that in his part of the presentation. And then last but not least, we have Dr. Nick Heredia, SafeTraces VP of R&D, who's a PhD molecular biologist and is going to be talking about emerging methods for performance testing. So just to briefly go through the agenda, Chip will talk to the first bullet here, upper room UVGI effects on pathogen control, followed by Bill, followed by Bill Bahnfleth, followed by Bill Palmer, followed by Nick, followed by a brief conclusion, and then some audience Q&A. And we're going to try to leave at least 10 minutes for that at the end here. Our goal for today's discussion is to be both educational on how UVGI works, but then also get to a lot of the big questions on this category of product technology out in the marketplace, particularly for those who own buildings or operate buildings, or those who are advising building owner operators on how to think about UVGI from both a technical and performance standpoint, but then also overlaying some of the cost, energy, and other considerations that go into deciding whether this is appropriate for a given building. So without further ado, I'm going to turn it over to Chip.
Great, thank you, Erik. Can you hear me?
Yes.
Great. All right. So I'm just going to start out with really basic information. So in general, what we want to do to start is to address, how do UVGI systems work? So we'll start with really just sort of a formal definition of what is ultraviolet or UV radiation. So there are a number of definitions of UV that exist in the literature, but perhaps among the most reliable are the definitions that have been provided by the International Union of Pure and Applied Chemists. And you'll see in the upper left, there are several different ranges of ultraviolet radiation that have been identified. UV generally represents the wavelength range from 100 to 400 nanometers. And then within that range, there are subdivisions that exist, including UVA, UVB, UVC, and vacuum UV, and their ranges are defined in the upper left as well. What we're particularly interested in these applications is germicidal ultraviolet radiation, which is nominally wavelengths of radiation between 200 and 320 nanometers. That's where we see damage largely happening within nucleic acids, including DNA and RNA. And then at wavelengths less than about 240 nanometers, we also start to see protein damage. I'll talk about both of those more in just a minute. More recently, there's been interest in what's informally termed far ultraviolet C radiation, which is, again, informally defined as radiation with wavelengths between 200 and 230 nanometers. So in that wavelength range, we see very effective disinfection, but minimal potential for damage to mammalian tissues, specifically exterior tissues like skin and eyes. And that's largely because at those relatively short wavelengths, proteins absorb very strongly, and that prevents those photons from penetrating very far into those tissues. And as a result, that's sometimes viewed, far UVC, as a game-changing technology. So the circle on the right sort of illustrates the part of the spectrum that we're going to focus on here. Next slide, please. All right, so next, let's consider what are the mechanisms of inactivation. I've already mentioned this briefly, but basically we're concerned with photochemical damage to critical biomolecules. Those include the nucleic acids, DNA and RNA, proteins, and in some cases, lipids. Again, this occurs with exposure to radiation in the wavelength range 200 to 320 nanometers. And the protein damage really is restricted to a subset of that at wavelengths below about 240 nanometers. So we do see wavelength dependence in the inactivation responses of microorganisms to UV radiation. And in a formal sense, we can describe that wavelength dependence using what's termed an action spectrum. So the action spectrum has been measured for SARS-CoV-2, the virus that causes COVID-19, and that's illustrated in the graph on the right. On the vertical axis, we see the inactivation constant for inactivation of that virus, presented on the horizontal axis as a function of wavelength. So the symbols that are included here are measured values of the inactivation constant at these various wavelengths. Now, superimposed on this graph is an absorbance spectrum for RNA. And the reason for doing that is that, first of all, SARS-CoV-2 is an RNA virus, so that is the nucleic acid. But we also see that there's a very good agreement between the RNA absorbance spectrum and the action spectrum, especially at wavelengths above about 240 nanometers. And those two start to deviate from each other at wavelengths below about 240 nanometers, largely because in addition to damage to RNA, we also start to see damage to proteins. Next slide, please. When we consider UVGI applications, there's really three general constraints that we need to be concerned with. First, obviously, we want to apply enough UVC radiation to accomplish acceptable pathogen inactivation. Now, it's not entirely clear what acceptable pathogen inactivation is, but it's likely that's going to be something that's going to be risk-based. And I'd be happy to try to answer questions related to that later on if there are some. So that's the first constraint. The second constraint is that we want to limit human exposure, especially skin and eyes, to below the threshold limit values, which have been established and recently updated by the American Conference of Governmental Industrial Hygienists, or ACGIH. And their TLVs are presented as a function of wavelength in the graph on the right. The red curve represents the most recent guidance that's been published for skin exposure, indicating what dose of radiation could you be exposed to in an 8-hour period as a function of wavelength. And the green curve illustrates the similar curve for the eyes. So the basic idea here is that we have information to describe what ACGIH have defined as acceptable exposures as a function of wavelength. So that's the second constraint. The third constraint is that we need to control air chemistry, and this is largely related to ozone and its photodegradation products. So there's a lot of work that's going on in this area right now, and really all I'm going to do in this presentation is just mention that we need to pay attention to air chemistry. Next slide, please. I'd like to, in this slide, present a simple model to describe the dynamic behavior of an upper room UVGI system. So I'm going to impose a number of assumptions here, and then I think Bill Bahnfleth will talk about, well, whether those assumptions are valid or when they might be violated. But for the time being, what I'm going to do is to assume that we're working in a well-mixed airspace. And if we have that well-mixed airspace, then it becomes relatively simple to develop a model to describe the dynamic behavior of this system. I've assumed also that there's a well-defined fraction of the airspace that's being irradiated, and I'll just call that lowercase f, and that's illustrated schematically in the upper right. The model itself that's presented on this slide, identified as the governing equation, accounts for advective transport of the pathogen of interest into and out of the control region, the room. It also accounts for natural decay. These viruses do die on their own. It accounts for inactivation by UV in this case, and then it accounts for the source term, or the rate at which the virus is introduced by an infected individual in the room. If we assume that the concentration of the virus in the air entering the room is 0, which is probably a legitimate assumption, we can come up with an analytical solution that's illustrated in the lower left to describe how the concentration of infective viruses in the air in the room will change as a function of time. And highlighted at the bottom left of this slide is a term alpha, which is the number of equivalent air changes per hour. That term accounts for the effects of physical air exchange, natural decay, and UV inactivation. And those processes are additive because they're all first order and they're independent. So if we consider that model, then on the next slide, we'll see what it implies about the dynamic behavior of these systems. So next slide, please. All right, so what I did was to apply the model to a setting that was a room with a volume of about 500 cubic meters and an occupancy of about 30. So this is sort of a typical classroom in a university setting or at an elementary school. I assumed also that 10% of the people in the room were infected and that they're what are identified in the literature as high emitters and emitting just by natural breathing. Under those conditions, such a person would be emitting something like 10 to the 5th viruses per person per hour. I assumed also that the air in the room was initially clean, meaning there were no viruses present before the infected people entered, and that the air entering the room itself is also clean. So in the graph on the right, there's an illustration of dynamic behavior. The vertical axis represents the concentration of infective viruses on a log scale. The horizontal axis illustrates time. And there's several things that emerge from this. If we look at the curve that's the top curve, that corresponds to 1 equivalent air change per hour. That's about the minimum condition that you could ever find in any setting, corresponding to very little physical air exchange, a little bit of natural decay, and no UV. Under those circumstances, we're going to get to a steady state condition in about an hour in a room like this. And its concentration is going to be on the order of maybe 500 or 600 viruses per cubic meter. At the other end of the spectrum, when we have, let's say, 200 equivalent air changes per hour, which is about the practical upper limit with SARS-CoV-2, which is what I'm simulating here, what we observe is that we get to a steady state condition much faster in just a matter of a few seconds. And the steady state concentration is a couple orders of magnitude lower than it was for the other case that I mentioned. And then obviously the intermediate values of the equivalent air change give us intermediate results. Generally, what we observe in these things is that we're going to get to a steady state condition fairly quickly in a well-mixed room, and that UV, or the incorporation of UV, which is required to get to those large number of equivalent air changes per hour, can reduce the risk of infection substantially. If you could just advance, please, that'd be great. So what I've illustrated here is, if we could, what I've illustrated here with this dashed line and the arrow is the 8-hour exposure that corresponds to 1 quantum of SARS-CoV-2, which would translate to something like 37% infection. So really, I've just put that on here for a reference point. And what's perhaps most important to recognize is that by using UV, you can go from a condition of having infection happening fairly easily to making it much more difficult to get infected. So if we could go to the last slide, please, just to summarize. Again, what we observe is that UVC is very effective for inactivation of airborne pathogens. The example that I gave was for SARS-CoV-2, but there's very similar behavior observed among most of the viral pathogens, including things like influenza. The implementation of UVC devices for airborne pathogen control is effective, but to date has been largely underutilized. Mixing conditions, or more generally fluid mechanics, are going to affect the distribution of these airborne pathogens and is likely to affect any engineering intervention that we include. And again, I believe Bill Bahnfleth will be addressing that. And then lastly, there's a need for standardization of design, testing, and validation. Thank you.
Thanks so much, Chip. So that level sets us in terms of, from a scientific standpoint, how UVC is working. And we appreciate everyone for hanging in there. I know in the audience we have some people who are deep on this, others who are coming to it a little bit newer, but now we're going to get into thinking about UVC vis-a-vis the mechanical and HVAC systems. And I'm going to now turn it over to Dr. Bill Bahnfleth.
Great. Thank you, Eric. So I'm going to talk about interactions with the air distribution and other factors in systems. I mean, we want to start from the point of view that we do have plenty of evidence that upper room germicidal ultraviolet is very effective, and that goes all the way back to the 1930s when studies like the one shown here that were done in the Germantown Friends School near Philadelphia were done by Wells, and Wilder. You can see on the right the difference between new cases of measles per week in classes that were treated with an upper room system and those that were not, and it was a very dramatic difference, and there are other studies that document that. So we'll just repeat that as groundwork and go to the next slide. The issue with upper room systems that's really kind of an important one is that they're very dependent on factors in the space that don't relate directly to how much UV energy we're putting into it, especially the air movement. We see on the left a typical upper room installation in a healthcare facility, and on the right a cartoon that shows how we create a disinfection zone above the occupied zone to keep from exposing the occupants to this potentially harmful radiation if it's 254 nanometers. So the way this system works, as Chip indicated, is we've got to get air to go from where the occupants are and where the contaminants are being admitted into this disinfection zone and then back. So clearly room airflow patterns will affect that. And this is much more complicated than an induct system where we can describe it in terms of a single pass efficiency, just like we can a filter. Next. So one of the things that's interesting about trying to control air quality from the point of view of infection transmission, airborne infection transmission, is that some of the things that we think we understand about air quality and air distribution are not necessarily true. And one of the things we've heard a lot in the last few years, maybe decades, is that stratified ventilation, displacement or underfloor that pushes contaminants upwards and out of a space is preferable. And there's actually some evidence that in general that's not true, but it's particularly not true for upper room UV systems. And there have been a number of studies that have looked at what happens when you either have a fan or don't have a fan in a space that has an upper room UV system. And this research that I'm showing here on this slide by Picharoff et al. Compared both CFD modeling and chamber experiments, and what we see in both of these figures is that whether it's upward flow or downward flow from the ceiling fan, there's a significant reduction in the amount of contamination when the fan is operating compared to when there's no fan. Next. And as I was saying before, mixing seems to perform better than displacement for upper room, and we've done some modeling of that here at Penn State. Young Bo Wan did the simulations that are the basis of what I'm showing here. We had a simple space that had a few people in it. One of them was an infector, and then 3 of them were receptors, and those were places where we measured levels of exposure. And we had an upper room system that was designed to the NIOSH guidelines for tuberculosis control. So for tuberculosis, it should do 20 air changes per hour, equivalent roughly, and a lot more than that for a virus that has a lower rate constant. And so we compared mixing ventilation at a typical level of 6 air changes per hour supply, about 1 CFM per square foot, with 0.7 air changes per hour of outdoor air. And then we also looked at overhead mixing at 0.7 air changes per hour, which would be like a dedicated outdoor air system, and displacement at 0.7. And what you see in the results on the right is that the black bars representing mixing at 6 air changes have by far the lower overall exposure. That's a logarithmic scale on the vertical. And we also see a significant difference between even an overhead mixing at minimum outdoor air system and a displacement system. So we conclude here that there's at least a 2x benefit to mixing based on this research that we did. Next. And I want to talk about another study here that I did in collaboration with Kishore Kankari, who many may have run into. He's a CFD modeling expert. And we collaborated on some simulations. Some of them have been published in an ASHRAE journal article. I'm going to show you some things from one that's been accepted but hasn't been published yet. And we've been looking at the effect of a number of parameters and their effect on the performance of an upper room system. So in this one, what we were studying was the effect of moving around the supply and return for the overhead mixing HVAC system in a space that had a couple of cubicles in it, and you see 2 groups of 3 people. One of them is treated as an infector. That's the mannequin with the red head at the in the upper cubicle in this isometric. So we had 3 air changes per hour of uncontaminated air coming through the space, and there are 2 upper room fixtures that you can see at the top of each of these. And we had 1 diffuser with a return in the corner, 1 diffuser in the center with return in the corner. Then we flipped the return and the supply around, and then we had 1 case where we had 2 supplies and 2 returns. Next. So this figure shows on the left some of the air distribution details, and we can see that even though this is an overhead mixing system, well mixed really is kind of a fallacy. There are some very complicated recirculation zones in this system. The 4 figures on to the right of this figure show something called the spread index, which is a metric that Kishore developed, which shows the fraction of the volume of a space that is above a certain level for whatever the variable is that's of interest. And what we're looking at here is age of the year, which tells us how long air has been in the space. So a high age of the year means that there's kind of a stagnant zone. And so we can see with the original case 1 layout where the diffuser is near the top in this plan view and the return is near the bottom, that we wind up with fairly low age of the year where the air is coming in and higher in the other cubicle. When we put the diffuser in the center, it goes up everywhere, and we actually get the worst performance with what you would think would be a good diffuser location because it's kind of symmetrical. When we move the single diffuser to the other end, then we get the mirror image of the pattern in case 1. And with 2 diffusers, we get slightly better performance, and both cubicles are a little better protected. So the point here is that even though we say we're doing mixing ventilation in all of these cases, and it's the same amount of air, we get quite different results in terms of where the air is stagnant and where it is relatively fresh. And the significance of the age of air that we used here as a criterion was that this was corresponding to 3 air changes per hour well mixed. Next. So now to make things even more interesting, instead of looking at the age of the air, now we're looking at the spread index for infection risk. We arbitrarily took 10% risk of infection in an hour. This system wasn't really designed to achieve a particular goal. So now we've got 4 cases with UV and 1 without. In the upper left, we see the original diffuser and return location, but no UV. And we have a fairly high probability of infection everywhere. You can see in the color contour plot directly below that, the big red spot, that's the cubicle where the infector is. So there's very high risk there and lower elsewhere. So now look at what happens when we have UV. Even though we're changing the airflow patterns a lot, the distribution of the UV energy doesn't really change very much. That's shown by the 2 figures at the far right that are, again, color contours. So the air distribution doesn't really affect what's going on with the UV, but if we look at the 4 figures in the middle with UVC, what we see is in every case, there's high probability of infection in the cubicle where the infector is, and it only varies by about a factor of 2. The best we get here is a spread index of 5.4%, and the worst is 11.8. So clearly here, the obstructions to flow created by the modular office furniture were a big factor independent of the air distribution. Next. And so that's what I want to say about performance and air distribution related effects. There's one other thing we need to talk about here in terms of HVAC is what we're going to do about the recent discussions of UV photochemistry, which starts with ozone but includes other things. And we've known for a long time that low pressure mercury vapor lamps produce potentially a wavelength of 185, a strong line there that can produce ozone. That's not really a problem for complying with UL 2998 as is now required by ASHRAE standard 62.1 and 62.2. All we have to do is select the right tube material to filter it out. What is new and being discussed a lot is other products of UV photolysis, and we'll see those on the next slide. So there have been some modeling studies, which is what we're talking about on this slide, and also some experimental studies that confirm the fact, which shouldn't be surprising, that UVC indoors has the potential to participate in photochemistry and produce byproducts, actually quite a few of them. So this is a modeling study by Penn et al. From University of Colorado, and they modeled many different potential reactions, and they showed the levels of the byproducts that were produced for 3 different levels of ventilation, low, medium, and high, or 0.33 and 9 air changes per hour. And what we see is that at higher ventilation rates, for most of the contaminants, the levels drop. And I won't point out individuals here in the interest of time, but it is interesting that if we put more outdoor air into a space, we are likely to get more ozone, and ozone is one of the most reactive things we can have indoors. So ozone levels actually go up as we bring in more outdoor air, and we get more OH radicals, more nitric oxide that may come in from outdoor air. So to me, this points out 2 things. One is we need to look at the levels of production of these byproducts enough to satisfy ourselves that we're ventilating or filtering effectively to remove them. And the other point that you could make here is that outdoor air is not the solution to everything, because it actually makes some things worse. So this is a bit of an emerging issue that we have to be aware of going forward. Next. So to summarize, I think what I've shown here will indicate that predicting the performance of an upper room system is a little more difficult than predicting the performance for an airstream disinfection system, but we know what the issues are. There are a number of ways in which HVAC affects the performance, and these need to be considered in design and operation. What kind of room air distribution do we have? What are the effects of the locations of supplies and exhausts, and the effect of furnishings? And then finally, this point about control of byproducts. And I think we can have high performance systems when we do consider all of these things, and systems are designed, installed, and operated well. But we have some work to do to have the tools to make this easy for everyone to do. Thank you.
All right, excellent. Thank you, Bill. Great job taking a lot of material and complicated material, distilling it down. We're now at the point in the webinar where we're going to go into the real world. And I think Chip and Bill have given us a great understanding of the technology and how it integrates from a system standpoint, and lots of considerations around that. Now I'm going to turn it over to Bill Palmer to talk about this technology and fixtures in real world environments. So the focus on 254, we know that he'll briefly touch on some of the other wavelengths and products, but the focus is going to be on 254, given that's most established. And Bill, just a note to you, we're a little bit behind schedule, so if you can kind of be as efficient as you can going through those, that would be greatly appreciated.
Great. Well, what I'm going to do now is focus more on the practical real-world application of upper room UVGI. And what should really jump out at us compared to other applications of UV lights, upper room UVGI is designed to be used in an occupied space. So you can see in the picture on the left, we're using upper room UVGI in a heavily occupied space where we are relying on convection currents and mechanical induced airflow patterns to allow the potentially infectious aerosols to travel up into the irradiated zone and be inactivated in that zone. And you can see in the picture on the right that we are creating a well-defined UV zone, irradiation zone in the upper portion of the room, but yet we're not allowing unsafe levels of UV into the occupied zone. Next slide. So what's probably not readily apparent in the previous pictures is how much we're actually flooding the upper portion of the room with UV light. And this is important because the effectiveness of upper room UV is a function of time and intensity. So the longer the period of time that a aerosol is exposed to UV energy, the greater the disinfection, and the higher the intensity, the greater the disinfection. So we're actually flooding a very large percentage of the room volume with UV energy, which is what allows this to be so effective. But at the same time, it's through the design of the fixtures that we're able to create this upper zone, high efficiency, high intensity, while maintaining a low amount of UV in the occupied space. Next slide, please. And we do that through the design of the fixtures. So typically, most of the upper room fixtures are separated into two categories. For lower ceilings, 8 foot to 12 foot, we would use a louvered or baffled luminaire. Whereas for higher room settings, 12 foot or greater, we would use typically a open or semi-open type of fixture. So looking at the louvered or baffled fixture in front of us, these depend highly on good optics, such as in this particular fixture, it has a parabolic reflector, which focuses a lot of the UV energy forward into the room, but light that comes off the front of the UV source could actually go out into the room at an undesirable angle and enter the occupied space, whether directly or as a reflection off of the ceiling. So to make sure that that does not occur, we place louvers or baffles in front of the UV source. And this takes blocks the UV energy that's coming out at undesirable angles so that it won't enter the occupied space and create safety issues. However, it probably reduces the total output from these fixtures by about 90%. So that 10% of output is sufficient to create a very effective disinfection zone in the upper room. But it also seems a bit wasteful. So what we do, next slide, for rooms with a taller ceiling where we're less concerned about reflection of the UV coming off of the ceiling and down into the occupied space, we can remove the louvers from the front of the fixture. And rather than blocking all of that, we can get all of that out into the upper portion of the room and allow it to go higher up. But we can, this particular device shows an extended tray at the bottom of the device so that we're still protecting the occupants in the lower portion of the room, but we're getting the full output of the fixture. So in this type of a fixture, we're probably utilizing 70% of the UV energy created by the device, so that one of these open devices can create a disinfection that's equivalent to 5 or 6 of the louver type of fixtures. So this makes it very applicable to these larger spaces that have higher ceilings, but yet we can still do it quite safely. Next slide. But for those people who are considering the purchase of upper room fixtures, it's important to have a checklist of requirements and recommendations that you want to see in every device that you purchase. First of all, every UV device has to be manufactured in an EPA registered establishment, and most building codes will require that UV fixtures are certified and listed to UL 1598 for electrical safety. And as part of that safety test, they also now include UL 8802 for photobiological safety, which tells us what should be a safe installation height for those fixtures with regard to skin and eye safety. As Bill already mentioned, UL 2998 shows that a fixture is ozone free, and this is mandatory in California and Canada, and it's also recommended by ASHRAE 62.1 and 2 and ASHRAE 241. And as Bill mentioned, 241 also recommends testing for the chemistry that could be created with regard to formaldehyde and particulate matter. And we usually would test these devices also against MS2, which is used as a surrogate for other infectious aerosols that could be, to show the effectiveness against infectious aerosols of the UV lights. And lastly, we have some IES test standards that we like to test the equipment to show the output of the device, because the actual UV output of a device is what we use to determine the dosing of a space. So how many fixtures of what type and size would we use in a given area based on their actual output. Next slide. So with regard to where these devices are applied, hospitals are full of both susceptible and infectious patients. So because of that, the use of UV has grown to include patient rooms, exam spaces, waiting areas. Next slide. And you have, likewise, in medical offices or dental offices, you have some of those same risks, but you also may have aerosol-inducing procedure or producing procedures, such as you have in the dental office. Next. And then when you look at any space where you're increasing the concentration of room occupants over a prolonged period of time, you're increasing the risk of transmission. Next. And also in areas like fitness centers, you have an increase in risk because the activity of the room people are working harder, breathing harder, expelling more aerosols. Next. In office spaces, if you have a large office space where you have a large number of people sharing that same space, they're sharing the same air, again, which increases risk. Next. And that is actually enhanced further when you take those people from the office and put them in a conference room. So now you have an even higher concentration of people and a higher level of risk. Next. And the same would be true for courthouses and town halls where people vote. Next. And of course, we're all familiar with being in a crowded restaurant where everyone is talking over the top of each other and creating, again, a increase in risk. And lastly, the next slide shows houses of worship, where it's kind of a combination of all of the worst things. You have a large number of people packed into a consolidated space, so you have a high concentration of individuals, but the activity in the room may include singing, which is one of the things that promotes creation of aerosols. So it again increases the risk. So all of these locations that were never really thought of for the application of upper room UV are now commonly used applications. Next. So from the information that both Chip and Bill showed, the scientific literature and the in situ testing has shown the effectiveness of upper room UV as an intervention. And what we've also been able to show is that of the interventions out there for equivalent levels of performance, upper room UV is probably the least energy intensive. So long-term, it's a great way to solve this problem. But there's also emerging technologies that are both emerging and here. 222 far UV, as is shown in the picture next door, can be, or to the right, can be used as both a upper room type of device, but can also be used as a whole room device, shining down into the room and irradiating surfaces as well as the air. And 265 nanometer LED devices are also starting to enter the market. But whether it's a 254 upper room fixture, 222 far UV, or 265 LED device, all of these devices are going to need better in situ testing to verify their performance in place. And with that, I'm going to go ahead and turn it over to Nick.
All right, that was excellent. Thanks so much, Bill. So lots of practical and valuable insights. I'm going to turn it over to our SafeTraces, Dr. Nick Heredia, VP of R&D, to talk about, to pick up on Bill's last point there about the need for better performance testing and level set us on what are those methods today and what's coming off on the horizon. So over to you, Nick.
All right, thank you. So what are the existing testing methods that we can use for these upper room UV systems? So typically you could do radiometric measurements, measuring the intensity of the light, but there's also limitations to each of these. So using that type of methodology really doesn't model the airflow in the room for the fixture, and it doesn't really account for air mixing behavior, as Bill Bahnfleth pointed out. MS2 phage, so that is a great mimic, a biological microorganism that you could spray, but it's unattractive and really impractical for use in situ at the installation site, because no one really wants to hear that you're spraying a bacteriophage in the environment. You could conduct test chamber studies, of course, and particle counters and model this, but the chambers really don't reflect the site-specific location and the variability that you'd have in that real-world dynamic. And particle counters are based on, or the particles are typically based on mass and not really on volume, and so it's difficult to get the dosage. You could do computational fluid dynamic modeling, or CFD, although this isn't really practical for every installation site, and it's theoretical and requires a lot of assumptions being made. Next slide, please. So, of course, recently ASHRAE instituted standard 241, and so this is control of infectious aerosols. This, I'll just point out, does not measure pathogen inactivation techniques that remove particles such from like UVC, but this is basically a methodology that would measure the equivalent airflow rate, or ECAI, of the occupied spaces. And so there are metrics in there to basically calculate the decay rate of the aerosol tracer particles versus the ECAI for spaces. It also introduces the concept of DNA tagged particles as qualified tracer particles to be used in this testing. And the testing measures all physical removal mechanisms, passive and mechanical ventilation, filtration, and deposition of these particles. But what if we could actually measure pathogen inactivation with technologies like UVC? So next slide, please. So DNA tagged particles, basically they're water-based solutions with known concentrations of uniquely identifiable pieces of DNA. And the DNA basically act as like barcodes. So you can follow these DNA particles and count them. They safely mimic airborne pathogen behavior. And the FDA, it considers it generally regarded as safe or GRAS. They can be sterilized, and it really correlates to inactivation dosages very well. DNA tagged aerosols can be selectively tuned to UV sensitivity, and they're used really to commission UV fixtures or air cleaning fixtures at their installation, and they would give you data in real world and dynamic conditions of that location. And performance data is expressed in dose-based log reductions and engineering metrics, such as equivalent air changes per hour, or that the airflow rate that we just talked about, the ECAI. UV contribution to air cleaning qualified is quantified. So you can actually count the DNA molecules. And that would give you a highly quantitative measure of what's going on in that room, and also measure what's happening with the HVAC and other technologies such as the HEPA filters, so filtration. Next slide, please. And so this is in situ data from one of our office spaces where we're actually utilizing our DNA tagged particles. And what we've done is we've created two different DNA tags, one that is relatively insensitive to UV. It's very similar to our current offering of our DNA tagged particles known as Veridart. And we've created another tag that we simultaneously aerosolize, and that tag is sensitive to UV. And so what we're seeing here is on the y-axis in a log 10 scale, the inactivation of the tracers, the DNA tracers over time on the x-axis. And so when we have UV off, there's just a natural decay due to ventilation and filtration in the room and the HVAC settings, and that's shown on the left. And both tracers, the dark blue and the light blue, track very well together. And on the right, we have the UV on. So we had a UV fixture on. And here you can see that the UV insensitive tag, the dark blue triangles, behaves very similarly and has the same essential log reduction as when the UV is off. But with the UV sensitive tag tracer, now you can see the effect and contribution of that UV light on that tracer in the greater decay of that those tagged particles. Next slide, please. And so following up on that, here we're showing a few things. So we're showing the testing of a air cleaning device. In this case, we have early data from a device from Cerazone. And this device is an air cleaner that uses several modes to clean the air. It has a filter. It also has ozone generation capabilities, and also some UV combination. And so we tested this device in a test chamber under controlled conditions, and we were looking at MS2 phage as the anchor point or standard. And here you see the equivalent air changes is what we're showing the data as. Air changes per hour. And so with the MS2 phage at the top, you see a 6.3 EACH. And we did a study with our Veridart air sampling technology that's on the market, and we get 3.6. And when we did the study, we actually broke it down into different particle sizes using an impactor study. So basically we can take very fine samples of the particles that are aerosolized and kind of see the distribution of and contributions of those particles at different sizes, from roughly like 10 microns down to 0.3 microns. And so importantly, I would say that when you look at the MS2 phage, you see that basically we're in the same ballpark with our UV insensitive tag, the very upper box, and then the middle box, and then the lower box demonstrates really the difference once you start incorporating our new UV sensitive tag, and how that really tracks well with the MS2 phage. And you see the delta between the UV insensitive tag and the UV sensitive tag, the middle and the lower panels, with these equivalent air changes per hour measurements. Next slide, please. Following up on that, we took this into the real world, and there were several studies done at the time of this early testing. We were using the Sarazone device that I mentioned earlier. And here we're looking at a commercial real estate space, retail space, that we were looking at the device off versus device on with that dual tag technology. And you can see that with the device off, you get about 4.7 in different locations, positions in the building, a 4.7 air change per hour, and at the right side, a 5.1 air change per hour in that retail space with the device off. And then when you turn on the device, basically you're getting a 6.6 air change per hour and a 7.4 with those two sites. And really what you're seeing is, number one, that you're having the device is having an effect on purifying the air by increasing the air changes per hour, the equivalent air changes per hour. And also that you can see the UV contribution. And as I mentioned, this device uses several technologies such as ozone and UV. So the UV contribution is a slight change, but this really shows you the resolution and granularity that you can get with the UV tag down to like 0.2 EACH and 0.4 at the different sample points. Next slide. So in summary, existing test methods they're good, but it really requires computational modeling or undesirable methods like releasing bacteriophage that are just impractical. There's limitations to the various existing methodologies for upper room UVGI. But emerging test methods could transform our ability to measure, verify, and really optimize the performance in real world situations. And the DNA tag particles are powerful, they're accurate, they're quantifiable, and they're really a great method for mimicking those airborne pathogen cases. So with that, thank you. Yep.
Thanks so much. So we went long, so I'm going to not really rehash all these conclusions. These are mostly things that have been mentioned by our previous speakers. So I want to get straight to some questions. We have a ton of them. Given time, we're not going to be able to get to all of them. And some of them are pretty technical in nature and probably best served by an email response. But I want to ask a question to the panel, which is, so you've made a case about the benefits of these technologies. You know, the data and research supports their efficacy from an infection control standpoint. There are some safety risks and other considerations, but why? So for the skeptic out here who's looking at this and saying, this sounds very complicated, why don't I just keep doing what I'm doing? And getting to this point of why has this technology, which is longstanding, been very underutilized? Why do you think that it has been underutilized, and why should people consider this in addition to just continuing to rely on the HVAC and mechanical systems? And I'll open that up to the whole panel. What's the case for this?
Well, I think one of the reasons why it's been underutilized is that primarily in the past, it's been used in a very small subset of commercial buildings, primarily tuberculosis applications in chest clinics and hospitals. So while it's been used very effectively in that setting, there aren't a lot of people who are familiar with those settings. And therefore, the perceived need for this type of device prior to COVID wasn't really there to drive the interest in the system. It's not that the system didn't work, it's just that people were unfamiliar with it.
Yeah, I think that lack of familiarity exists today, remains today, and I think is one of the major reasons why this technology has not been employed to the extent that it should. But it's also very clear now that relative to the other engineering control measures that are available, UV is the least energy intensive, probably the least expensive in terms of capital and operating costs, and the most effective. I think it has the potential, especially against things like the coronaviruses and influenza viruses and measles virus, for that matter, most airborne viruses. It has the potential to impart much greater inactivation, or let's say protection, than any other technology, and it's not even close.
Okay, great. Well, we've got a minute left, and I feel very bad about shortchanging Q&A, but we will just have to respect time here and get back to people via email. I want to just say a couple closing announcements. So for SafeTraces, for anyone who's involved in UVC, and particularly product manufacturers, service providers, and researchers, for those who are interested in our kind of testing and analytics method and platform that Nick introduced here, please contact us. We're working with people in a variety of different research and commercial collaborations. So you can contact me directly at eric@safetraces.com. We have monthly educational webinars. So last month we did a webinar on ASHRAE 241. In the next couple months, they're going to be more industry focused on healthcare and education. And then we also have certification trainings for those who want to be practitioners and users of our technology. And there's some information up here. To reach out to any of the folks on today's panel, here are all their email addresses. We'll be following up with links to the recording here for everyone registered, and put that up on YouTube. So we hope you reach out. We hope this is valuable. And we will capture all the questions that came across chat, and apologies again for not having the time to get to those. So on behalf of the panel, on behalf of SafeTraces, thank you all for attending today. Great discussion, really complicated topic that an hour doesn't really do justice to, but we packed a lot in here, and hopefully it was helpful and valuable to you. Thanks so much.